So our next speaker is Alex Rice, who will talk on constructions related to well-known distance problems. Go ahead, please.
Thank you, as always, to Mel and the organizers for the invitation to speak here. I believe this is my 8th time speaking at CANT over the past 12 years. It's always, I miss being together with everybody in New York. It's always one of my favorite things every year. So this talk will be very different from any of those other 7, not only because it's the first virtual one, but also content-wise. I'm going to talk about a couple little bite-sized projects from the summer of 2019. The first of which came from an undergraduate research experience that I did at Millsaps College, which is in Jackson, Mississippi, with these 6 Millsaps undergraduates. You can see their names there on the title slide. I should say they were Millsaps undergraduates then. They've all moved on to bigger and better things now, but for 5 magical weeks in the before times during the summer of 2019, we were all together doing math, and the math we were doing was mostly centered around the Erdős distinct distance problem. So that is, if I give you a natural number n, what is the minimum number of distinct distances that can occur between those n points? So just for the simplest example, if n were 3, you could arrange the points in an equilateral triangle. So f of 3 would be 1. But as soon as you add a 4th point, the best you could do as far as minimizing would be to have 2 distinct distances. So f of 4 would be 2. In that original paper of Erdős, he gave asymptotic upper and lower bounds, one of which is just a very direct and simple pigeonhole argument. That says that f of n is at least the square root of n. Literally, those 2 little lines there are the whole argument. By the way, by those little Vinogradov symbols here, all I mean is that I'm potentially hiding a multiplicative constant. But then as far as an upper bound on the minimum, for that you would need a construction, and the natural construction is a grid in the integer lattice, because distances between integer lattice points, they're all square roots of integers, but specifically integers that are the sums of 2 squares. And so this is the counting function for the integers that are the sums of 2 squares up to n. So that's where, that was sort of the starting point. And a lot of the work, really robust literature developed over the next 60 years or so. And a lot of the work in that direction was all about asymptotic, sort of the asymptotic order of growth of this quantity as n grows to infinity. And that was more or less resolved by Guth and Katz after many, many years, who got a lower bound that almost matches that upper bound that comes from the integer lattice. So as far as asymptotic order of growth, that's basically the resolution of the problem. But what if you weren't really interested in asymptotic order of growth? What if you were interested in exact answers for fixed values, let's say a fixed number of points, and you really wanted to get your hands on examples? Because f of n is a sublinear function, if you wanted to do that, it would actually make a little more sense to take the inverse perspective. What I mean by that is, instead of fixing the number of points and asking for the minimum number of distances, you could fix the number of distances and ask for the maximum number of points. And also, if you wanted to be even more ambitious, you could try to classify the configurations that achieved that maximum. So that was sort of the problem laid out by Erdős and Fishburne, a full 50 years after the original Erdős distinct distance problem paper. Just to clarify the definition of this function g and the inverse relationship, that pigeonhole argument that says that f of n is at least root n is equivalent to saying that g of k is less than k squared. If you have k distances, then up to a constant, you could have at most k squared points. But like I said, my motivation for looking at it from this inverse perspective is not to look at asymptotics. I want to look at exact values for specific cases. And that turns out to be pretty difficult. It's only been resolved up to k equals 6. And as k gets a little bit higher, you start to see these lattice configurations, not the regular integer lattice, but like a lattice made of equilateral triangles. So for example, if you have 5 distances, the best you can do is 12 points. And this exact configuration that I have very roughly drawn here is the only way to do it. Here and throughout, anytime I say that a configuration is unique for this sort of problem, I of course mean up to scaling or any sort of distance preserving transformation. That's pretty much, that's the only way you can get those 12 points with only 5 distances. But for k's greater than 6, this is still a wide open problem. An approach that I wanted to take in this summer research program a couple of years ago is, well, what if you just change what you mean by distance, right? If you look at a sort of alternative metric space, if you have an alternative metric, then you get a different version of the Erdős distinct distance question. Okay, this is not a brand new idea. Julia Garibaldi did work related to this, specifically with metrics determined by norms defined by convex bodies with non-vanishing curvature, etc. And a lot of that also appears in the book on the Erdős distance problem by Julia Garibaldi, Alex Josevich, and Steve Sanger. And then even as recently as this past summer, so after the summer that I'm talking about, Adam Scheffer's Polymath RU group did work on the Erdős distinct distance problem and like a pin distance problem for LP metrics. But I wanted to focus on a really specific and kind of easier metric, at least in this context, which is the L1, the metric induced by the little L1 norm, so the taxicab metric. So I've given the definition here, but intuitively, the way you should think of the L1 metric is if you want to get from point A to point B, how far do you have to travel if you're only allowed to walk parallel to the coordinate axes, sort of as if you were on like a grid of city streets. And we looked at this metric in all dimensions. So I've just drawn a couple pictures here. Because we have a new notion of distance, we have a new notion of what it means to talk about a circle or a sphere. So this is a circle, quote unquote, in 2 dimensions, a sphere, quote unquote, in 3 dimensions. It's this like octahedron. In general, you're going to get this 2 to the d faced polytope with a face for every choice of sign for each of the d coordinates. I think the fancy word is orthoplex, or I've seen a couple other fancy words, but yeah, that's what the spheres look like now. So the reason why I introduced this kind of precise inverse formulation before talking about the taxicab metric is, if you look at the original style of Erdős distinct distance result, which is about an asymptotic order of growth, in that context, the L1 metric problem is completely trivial. And here's why I say that. The norm, because the norm is flat, and because it respects the integer lattice, by which I mean distances between L1 distances between integer lattice points aren't just square roots of integers, they are integers. So when you look at an integer grid in d dimensions, all of those distances between those points are integers bounded by, d times n to the 1 over d. Meanwhile, on the other side, the same pigeonhole argument that Erdős used for the usual distance still works in the L1 context. So you actually have the same order of growth on both sides. The integer lattice actually achieves the same order of growth that you get on the other side from the pigeonhole argument. So looking at it from the inverse perspective, if I gave you k taxicab distances in RD, and you wanted to know what's the maximum number of points, as far as order of growth goes, the answer just is k to the d, and there's not really anything else to do. But if you wanted to answer the question exactly, well, then there might be some more to do. So I mentioned the simplest case of 3 points determining one distance, right, which is an equilateral triangle. If you wanted to know the fastest way to prove that, I mean, other than just saying it's a standard fact of Euclidean geometry, I would say, you'd say, okay, take 2 points, X and Y, say they're separated by distance 1. If I'm only going to use that same distance, every other point has to lie on both the circle of radius 1 centered at X and the circle of radius 1 centered at Y. Those two circles intersect at 2 points, but those 2 points are too far apart, so I can only take one of them. I can't take both of them. I could use that exact same idea with the taxicab metric. And everything works out the same. The circles look different. They still intersect at 2 points. But what's different is if the original 2 points were axis parallel, if their difference vector is parallel to a coordinate axis, then both of the intersection points of those 2 circles are actually that same L1 distance apart. Okay. So even just with one distance, looking at the taxicab metric gives you something different. Instead of g of 1 being 3, now g of 1 is 4. And this 4-corner configuration is the only way to do it, up to, distance preserving transformation and scaling. Okay. So that's simple enough. And how does it generalize? It turns out that it generalizes very nicely in 2 dimensions. And probably the easiest way to see that is to use a connection between the L1 norm and a norm that's even simpler in this context, which is the L infinity norm. So just the max norm, the norm that takes the maximum of the absolute value of the coordinates. So in 2 dimensions, an L1 circle is this rotated square, whereas an L infinity circle is just a regular axis parallel square. If you wanted to get real official about it, you could say the 2 norms are related by this linear isometry. Here I'm kind of using x, y as coordinates, and here I'm using x as a vector. But that map is a linear isometry, basically just rotating and scaling a little bit. So anything that you prove in the context of one of these Erdős type problems in the L infinity norm in 2 dimensions, you automatically get it for free also in the L1 norm. And you can induct on the number of distances and show that for the L infinity norm, k distances in R2, the best you can do is just a grid, a k+1 by k+1 square grid in the integer lattice. And so that means that that's also the answer, k+1 squared, for the L1 norm, except instead of the axis parallel square grid in the integer lattice, it's this rotated grid of k+1 squared points. And so then we'd be like, okay, let's go to higher dimensions. And this same idea generalizes very nicely for the L infinity norm. It's very intuitive that the answer for the L infinity norm would be just take all the integers up to k in each dimension. You've got basically a cube chunk of the integer lattice. So you've got k+1 to the d points. No way to do any better than that. And that is true. That same induction argument works in all dimensions. But if what you were really interested in is the L1 norm, that doesn't help, because this equivalence between the L1 and L infinity norm in 2 dimensions breaks down in higher dimensions, right? I already mentioned that in 3 dimensions, an L1 sphere is this octahedron. And so, basically the punchline here is, for d greater than or equal to 3, 2 to the d is not the same as 2d, right? Because an L infinity sphere in any dimensions is basically a cube. So you got to do something different if you want to generalize this definitive answer in 2 dimensions for the L1 norm. You've got to do it differently other than just appealing to the L infinity norm. And that's what this definition does. This is what we determine to sort of be the right generalization of that rotated square grid of points in R2 for the L1 metric. What we're exploiting here is that when you take the L1 norm, the L1 distance between two integer lattice points, all the absolute values you're taking and all the negative signs you're using, those have no impact on parity. Which is to say, if two integer lattice points have this, if their L1 norms have the same parity, then their L1 distance will always be even. Okay, and so what we defined here is lambda d of k. It's the integer lattice points on every other L1 sphere of integer radius, decreasing starting with radius k. So here's two quick examples. Lambda 2 of 3, that would be R2, 3 distances, 3 taxi cab distances, right? So you take all these points along the outside are the integer lattice points of L1 norm 3. These open circles are the ones I'm not taking. Those are the points with L1 norm 2. I am taking the points with L1 norm 1. I'm not taking the point, I'm not taking the origin. And notice what comes out is this 4x4 rotated square, just like we talked about on the previous slide. So that's 16 points in R2, determining 3 L1 distances. And that does generalize. So here's lambda 3 of 2. So R3, but only 2 distinct taxi cab distances. So I start with all the points on the integer lattice of L1 norm 2, and then I add in also the origin because 0 is congruent to 2, not 2. This is 19 points. So, think of this as a 3-dimensional city, and these are all the houses on each of those blocks, on each of those intersections. Every pair of those houses is either 2 blocks apart or 4 blocks apart. There's no other distances, even though there's 19 points, which, is kind of a lot. The pencil markings are meant to be the Z coordinate level sets. So we have the points in the XY plane, the points at Z equals 1, etc. Okay. So that's a perfectly good construction, but what is actually true in general about these sets lambda d of k, which are they're meant to be our candidates for optimal configurations for the Erdős distinct distance problem with the taxicab metric. So what can we actually say about them? So this is these next two theorems are joint with my 6 undergraduate at the time co-authors from Millsaps: Vidresh Balaji, Olivia Edwards, Anne-Marie Lofton, Solomon Macharo, Lo Phillips, and Biniam Sagai. So first of all, lambda d of k does what it's supposed to do in that it determines exactly k distinct L1 distances. It's exactly like I said. By the triangle inequality, they're all bounded by 2k, but also by this parity observation, they're all even. So there's only k of them. The other important thing for the context of this question is how many points are there in this set in general? And this is a little messy, but a key here is this recursive formula. If I draw your attention to the right-hand side of item 2. Let me go back one slide. The idea of that recursive formula is if you look here at lambda 3, 2, if you look in the XY plane, that's a copy of lambda 2, 2, right? 2 distances in R2. Then if I go to Z equals 1, that's a copy of lambda 2, 1. And then at the top, you have a point, that's a copy of lambda 2, 0. So, and of course, the middle and the top also have their mirror image down below with negative Z coordinates. So this first term is meant to be the slice in the middle, and the summation are the 2 slices at each level on the top and the bottom. So that gives you a recursive formula for the number of points in these sets. And then what you can do is you can appeal to classical formulas for sums of powers, right? Because, you know, if in 2 dimensions it's k plus 1 squared, then if you're going to get to 3 dimensions, you're going to be adding up a bunch of squares, et cetera, et cetera. And so I won't get into all the details here, but the size of lambda d of k is a polynomial in k plus 1. It's degree d, and it only has exponents that are congruent to d mod 2. There's a recursive relationship between the coefficients, and the leading coefficient is always 2 to the d minus 1 over d factorial. So that's a little bit messy. I think maybe it'd be best to just show a few examples. So this is a table that has on the left side the dimension, and on the right-hand side the number of points in this set, which determines k distinct L1 distances in RD. And what I claim is that this is a good candidate for the absolute dead-on perfect answer to the question of what's the maximum number of points you can have with only k distinct L1 distances in RD. Not only that, it's the unique answer up to similarity. But were we actually able to prove that? The answer is kinda. We were able to prove some stuff. So same Millsaps group. Dimension 2, it's all good. Like we said, based on that equivalence with the L infinity norm and that induction argument. In dimension 3, it does work for a single distance. So if you have a single L1 distance, this 6-point configuration is the best that you can do. That was previously known via graph theory. Our proof is more direct and elementary. You basically just say, start with the southernmost point. Every other point is on a single upper hemisphere centered at that point. Then you just do some case analysis on how can a bunch of equidistant points be distributed on the faces of an upper L1 hemisphere? And do a lot of case analysis, and this result pops out. Okay. But if you really ask me, why do I feel so confident about that this is the real unique answer to the question, I would say it's this item 3, which is we were able to prove a conditional result, that lambda d of k is uniquely maximal up to similarity for all dimensions and all number of distances, provided all such maximal sets determine their largest L1 distance parallel to an axis. Okay. I'm going to switch my screen share for a moment just to say a little bit about that, which is, what do I mean by parallel to an axis? I mean, let's say you have a set and your largest L1 distance determined by the set is lambda. Then it should be that you should be able to find 2 points, x and x plus lambda times a standard basis vector. Okay. If this were the regular distance, you could just rotate, but the L1 norm is not invariant under rotation, so you can't do that. But if you did have that, then you would say every other point is contained in the ball of radius lambda. It's so weird to say ball and then draw that picture, but that's what our balls look like. Every other point is contained in the 2 L1 balls of radius lambda centered at those 2 points. And what's nice about the L1 metric is if you have 2 points axis parallel and you intersect these 2 balls, you actually get another L1 ball of radius lambda over 2. And then because you have this point at the North Pole, you can just look at the level sets on this upper hemisphere. And I'll say you can induct on D. You can induct on D to count these points, assuming you've already done the problem in dimension D minus 1. Then if you remove these points, why would I remove those points? if I have all of my points contained in this single ball, and I remove the points on the upper hemisphere, I have actually removed the longest distance from the set. So now by removing these points, you're down to k-1 distances. And so you induct on k. I wish it were really that simple to write down. That's really the main idea. It turned out to be a little bit messy to write down that conditional proof, but the one thing that's missing is we don't know for sure that we can assume that we have both of these points in the set. I'm going to very, very quickly say one more thing, just because I wanted to call back to something from CANT from a couple years ago. And I really will just take maybe 2 minutes. CANT 2 years ago was a memorial for Jean Bourgain. And there's this really nice result of Jean Bourgain and others independently, that if you have a positive proportion of the plane, then that set has to determine all sufficiently large distances. And you could avoid 1 or 2 distances or any finite collection of distances, but eventually there's going to be a threshold where you have all the distances. Okay. Something that you could ask is that positive, and actually a question that Alex Yosevich asked me at that time, is that hypothesis actually sharp, that you need a positive proportion, or could you replace this with something quantitative like 1 over log r? And I'll be very quick and just say, the answer is no, you can't. For any density function decaying to 0, no matter how slowly, you can actually find the set that misses an unbounded collection of distances, and at least along that sequence tending to infinity, the density of your set is greater than f. So you could think of f as like 1 over log r. And that construction generalizes to any dimension and any metric induced by a norm on RD. And what does it look like? It looks like a bunch of chunks of thickened integer lattice points, where the scale of the chunk is determined by the previous radius. So you can avoid this collection of distances and then choose your scales big enough so that your density decays as slowly as you want, at least in this limb soup sense. Okay. And yeah, so this just says something about why that set really doesn't have any of those Rn distances, and it generalizes to any dimension and any metric. So in that sense, the Bourgain result is sharp. You cannot do any better quantitatively than positive upper density. And I will stop right there.
Thank you very much, Alex. I think we have to move right on to our next speaker, with Sinai Robbins. So Sinai, if you can share the screen with your slides,